Welcome to a fascinating journey into one of science's most profound and revolutionary discoveries, chaos theory. Today we'll explore how hidden patterns emerge from apparent randomness, reshaping our understanding of the universe itself. What if I told you that the flutter of a butterfly's wings in Brazil could set off a tornado in Texas? Or that the irregular beat of your heart follows mathematical patterns similar to those found in weather systems? These aren't just poetic metaphors. They're scientific insights that have transformed our understanding of everything from weather patterns to the human brain, from financial markets to the very fabric of the cosmos. Our story begins in 1961 at MIT, where meteorologist Edward Lorenz made an accidental discovery that would revolutionize science. While running weather simulations on his computer, he decided to take a shortcut. Instead of entering the full number 0.506127, he rounded it to 0.506. This tiny difference, less than a thousandth, should have produced nearly identical results. But when he returned from getting coffee, he found something astonishing. His weather predictions had diverged dramatically. This discovery led to what we now call the butterfly effect, the notion that minute changes in initial conditions can lead to vastly different outcomes over time. But Lorenz wasn't the first to glimpse this phenomenon. Decades earlier, the brilliant mathematician Henri Poincaré encountered a similar puzzle while studying the three-body problem in celestial mechanics. He found that predicting the motion of just three gravitating bodies could lead to chaos, challenging the deterministic worldview that had dominated science since Newton. What makes these discoveries so revolutionary is that they revealed a new kind of order, not the rigid clockwork universe of classical physics, but a universe where structure and pattern emerge from apparent randomness. When Lorenz plotted his data, he discovered beautiful, never-repeating but always similar patterns that we now call strange attractors. To summarize this chapter, chaos theory emerged from the realization that small changes can have enormous consequences, and that within apparent disorder lies a deeper form of order. These insights came from both meteorology and mathematics, showing how fundamental these principles are to our universe. Let's dive deeper into where chaos theory has had its most visible impact: weather and natural systems. Modern meteorology is built on the understanding that weather is a chaotic system. This doesn't mean it's random. Rather, it follows precise physical laws, but with such sensitivity to initial conditions that long-term prediction becomes increasingly difficult. Consider a hurricane forming over the Atlantic. Its spiral structure is no accident. It's a natural expression of chaotic dynamics, where air pressure, temperature, and moisture interact in complex ways. Yet within this complexity, we find fractals, patterns that repeat at different scales. Look at satellite imagery of a hurricane, and you'll see smaller spiral formations within the larger spiral, each following similar patterns. These fractal patterns appear throughout nature. Look at a coastline on a map, then zoom in. You'll find similar jagged patterns at every scale. Examine a snowflake under a microscope, and you'll discover intricate geometric patterns that emerge from chaos. Even the branching patterns of trees and river systems follow fractal mathematics. To recap, weather systems demonstrate how chaos theory bridges the gap between unpredictability and pattern. While we can't predict exact weather conditions far in advance, we can understand the underlying patterns and improve our short-term forecasts dramatically. Our bodies are masterpieces of organized chaos. Take your heartbeat. While we often think it should be perfectly regular, a healthy heart actually shows subtle variations in its rhythm. This heart rate variability is a sign of health, allowing our bodies to adapt to changing conditions. When the heartbeat becomes too regular, it can actually indicate problems. This insight has revolutionized cardiology. By analyzing the chaotic patterns in heart rhythms, doctors can now predict certain types of cardiac arrhythmias before they become dangerous. Similar principles apply to brain activity. Epileptic seizures often show characteristic changes in the brain's chaotic patterns before they occur, opening new possibilities for prediction and treatment. One of the most striking examples of chaos in biology is found in population dynamics. The classic example is the relationship between predators and prey. When prey animals become abundant, predator populations grow. This reduces the prey population, which then causes predator numbers to fall, allowing prey to recover, creating an endless dance of boom and bust cycles that never exactly repeat. To summarize, biological systems thrive on the edge of chaos, using controlled unpredictability to maintain health and adaptability. Understanding these patterns has opened new frontiers in medicine and ecology. Financial markets are perhaps the most visible example of chaos theory in action. Stock prices follow patterns that appear random at first glance, but contain hidden structures. Just as a double pendulum swings in unpredictable yet mathematically determined ways, market movements follow complex patterns influenced by countless interacting factors. Consider the stock market crash of 1987, known as Black Monday. Traditional economic models couldn't explain why markets worldwide fell so dramatically. Chaos theory offered a new perspective. The crash emerged from the complex interaction of automated trading systems, human psychology, and market structures, demonstrating how small triggers can cascade into system-wide effects. In technology, chaos theory has found surprising applications. Internet traffic follows chaotic patterns that help in designing better networks. Encryption systems use chaos to generate secure codes. Even the way information spreads through social networks shows chaotic behavior. To recap, economic and technological systems demonstrate how chaos theory applies to human-created systems, helping us understand and work with their inherent unpredictability. Art and chaos have a fascinating relationship. Jackson Pollock's famous drip paintings, once dismissed as random splashes, have been shown to contain fractal patterns similar to those found in nature. These patterns may explain why his work resonates so deeply with viewers. We're naturally attuned to recognize these forms. In music, composers like Xenakis have used chaos theory to create compositions that balance structure and unpredictability. Modern digital artists use algorithms based on chaos theory to generate artwork that mimics natural forms and patterns. These works often feel both familiar and surprising, just like the natural world they emulate. To summarize, chaos theory reveals how creativity often emerges from the balance between order and disorder, whether in nature or human artistic expression. Let's address some common misconceptions about chaos theory. First, chaos doesn't mean complete randomness. It describes systems that are deterministic but sensitive to initial conditions. Second, chaos theory isn't just about weather. As we've seen, it applies to virtually every complex system. Common questions include, does chaos theory mean we can never predict anything? No. It means we need to understand the limits of prediction and work within them. Is chaos always bad? Not at all. Chaotic systems often lead to innovation and adaptation. Can we control chaos? While we can't always control chaotic systems, we can often influence them by understanding their patterns. To recap, chaos theory is often misunderstood, but its principles are both more precise and more widely applicable than many realize. Let's explore some visual demonstrations of chaos. The double pendulum, one pendulum attached to another, shows how simple mechanical systems can produce complex behavior. Watch how it never repeats exactly the same pattern, yet stays within certain boundaries. The Mandelbrot set, perhaps the most famous fractal, demonstrates infinite complexity emerging from a simple mathematical formula. As you zoom in, you find copies of the main pattern repeating at ever smaller scales, each slightly different yet recognizably similar. To summarize, these visual examples help us understand how simple rules can generate endless complexity and beauty. As we conclude our exploration of chaos theory, we're left with a profound appreciation for the delicate balance between order and disorder in our universe. This isn't just abstract science, it's a new way of seeing the world around us. From the swirl of cream in your coffee to the turbulence of distant galaxies, chaos theory reveals the hidden patterns that connect all things. Understanding chaos doesn't diminish the wonder of our world, it enhances it. It shows us that unpredictability isn't a flaw in nature's design, but a fundamental feature that drives creativity, adaptation, and evolution. As we face an increasingly complex world, these insights become more valuable than ever. I encourage you to look for these patterns in your own world. Remember, within every apparent chaos lies a hidden order waiting to be discovered. Thank you for joining me on this journey through one of science's most fascinating frontiers.